All right, thermal kids, listening up. Everybody else, you can just kind of hang tight quietly until Ms. Brooker comes by and grabs you to be little movers. Okay? Just gonna grab as many as she can, I guess. What is it? Many hands make light work. That's the saying. So she's probably gonna grab a lot of you guys. Okay. So let's talk about the bottom question, and then I'll go back up to the top one. All right. So in enthalpy, we've been talking about the 3 different types of calculations you're going to get for that type of question. And the one before that was Hess's law. So separate from Hess's law, the enthalpy questions is looking at heat capacity of water and using that to figure out enthalpy because you're calculating the energy change. 3 different types. First type that we talked about was the burning of a fuel and heating water and using that to figure out how much energy is released from the burning of that fuel. The second one that we talked about was the mixing of the 2 solutions together, which is also known as the neutralization enthalpy one. That one has not come up in a very, very long time. The last time I saw it was 2013, and that was actually before I was a teacher. So unlikely for it to pop up, but I see it a lot in the SciPad for some reason, so I wanted to go over it just in case. The third one, which this one comes up more frequently, and the burning fuel one does, is the dissolving of an ionic solid into a solution to then figure out the enthalpy change. So first off, we are thinking about dissolving something in water, and we're looking at potassium nitrate. And it says that in this case, the temperature is decreasing. So this is our first time seeing one that actually does decrease. Everything else we've seen so far is increased. And we see it go from 21.3 to 14.2. So that is our delta T. That's our change in temperature. They want you to calculate the mass of the sodium nitrate that must dissolve to get that temperature decrease. And they said assume the heat capacity of the potassium nitrate solution is the same as what the heat capacity is for water. So that's C. They also want you to assume that the mass of the sodium nitrate solution is 138 grams. So that there is going to be the mass of the water. Remember, we want to keep everything in check. This is a slightly different question because they've ordered it a different way, because what they're asking for in this case for the unknown is to calculate the other M, which is our question mark, and that's the mass of whatever is being dissolved. Oh my God, what is going on? This whole thing is like, why is it like so blurry? Why does it keep, is it just because of the fluorescent lighting in this room? All right. So that's slightly different than what you guys are used to. So in this case, since the M is the unknown, what we're going to be given is the enthalpy, which they have given us up here. So this is our delta H. So they have given us delta H instead. Delta H is the change in heat energy, enthalpy. All right, similar steps, just a slight different tweak. So first thing we need to figure out is our Q value, because that tells us the heat exchange. So Q is equal to the, no, I'm trying to remember, M times C times delta T. They will give you the equations on the assessment, so don't worry about memorizing them. So Q would equal the mass of my solution, so that is 135 grams, times the heat capacity of water, which is 1.48 joules per gram per degree Celsius. And then my temperature change is the difference between the 21 to the 14. So 21.3 minus 14.2. So I have a change as negative 1.7 degrees Celsius. It's a decreased temperature. Make sure you're showing all your working, because if you make a mistake somewhere, I can backtrack and figure out where it was and still give you some points. If you do not show me any working, I cannot backtrack and I cannot help you. So Q is equal to negative 4,006.35 joules. So that's the joules that have been released. We got to be mindful that the enthalpy above has been given it to us in kilojoules, so we need to convert this into kilojoules. In order for me to do that, I divide by 1,000. So divide it by 1,000, and we get Q equals negative 4.00653 kilojoules. Are we happy with how I got to that number? No? Where do you want me to backtrack to? Oh, 7.1. I got this by doing 21.3, and I subtracted 14.2. 21.3 minus 14.2, 1, and then, am I doing the math right? 21 minus 14. Yeah, that's 7. And it's a negative number because we're talking about decrease in temperature. Yep, it's decreased. It's endothermic. Just trying to find the Gibbs free energy equation for you. That's the equation one. All right, keep going. Cool. Okay. Next equation that we talked about was the one for enthalpy. So delta H is equal to the negative Q divided by the N value. Usually what we've been having in most of these equations is you've been trying to solve for delta H. In this case, we are actually solving for N because that is our unknown. We don't know the mass of these potassium nitrate that we have dissolved. So just be mindful that don't get into the habit of always using the equation in one way because they might switch it up for you. That's why it's really important to use those collated questions from No Brain Too Small because it does actually show how they ask the same question in different ways. This is the same question. They just want you to answer it in a different way. So I'm now going to solve for N instead. So I want to isolate N by itself. You have two choices. You can plug in the numbers now and solve it mathematically, or you can move the variables around first and have it so that N equals the answer. Any preference? Move the variables around? Okay. So if I want to get rid of the N and put the N by itself, I want to multiply each side by N. The N's then cancel out. I get N times delta H equals negative Q. We good? All right, then I want to get rid of the delta H. I'm just going to change colors to help you guys see my steps. So divide by delta H, divide by delta H. Delta H now cancels out, and I get N equals negative Q divided by the change in enthalpy. Now we just plug in our numbers. So N equals negative 4.001653 kilojoules. I personally like to keep it unrounded till the very end. We divide by our delta H, which was given up here. So 4.9. And in fact, since that's negative Q and that was a negative number, this now becomes a positive. And that's divided by 34.9 kilojoules per mole. I like to write down the units because then it helps me double check that I've done everything correctly. Kilojoules and kilojoules cancel out, and I have per mole, which means I have mole again. So let's do that math. I like my math. Math R usually means that we're going to get an easy question. So 653 divided by 34.9. I get my moles to be 0.1148, and then there's lots of repeating numbers, so I'm just going to write that for the time being. So that's how many moles I need. I don't know if I have space in the back. The back? Blank? Yes, it is. Cool. All right. Last thing I'm then going to do is I need to convert this into mass, because right now it's asking me, I have moles, so I have amounts, but I need to calculate the mass. I'm going to be using the molecular mass of the potassium nitrate, which is 101 grams per mole. So if you guys remember, N equals, oopsie, can't see it now, N equals little m divided by big M. We're rearranging so the m's by itself. So multiply both sides by big M. Big M cancels out. I have M equals big M times little m. Yeah. We good? Okay. Plug in our numbers. M equals 101 grams per mole times the 0.1148 moles. I try to leave things I don't clear my calculator, so that way I'm able to then, I'm then able to just plug in and do my multiplication, so 101. So I get my mass is equal to 11 point, and now I'm going to round it to 3 significant figures, so 11.6, because I'm rounding up. And that's my final answer. Nice. Oops, sorry, you guys can't. Let me pull up the NZQA website so we can actually see the marking schedule. This one is the 2021 exam. Hopefully the internet decides to play nice. And then I'll talk about the last theory question that we have, which I think is actually pretty cool. And also a good excuse to leave your room messy. We want the 2021 schedule, and this was question 1C. 1C. There we go. Miss got the right answer. That's going to go as a good sign. All right, 11.6. Yay, Miss taught it correctly. Okay. Here we go. So the breakdown of these points: correct mass of potassium nitrate with the units, with the significant figures. That is your excellence. So what I've written down there, that is excellence without any kind of justification. It's all just math. If you did one error in your processing, you would get a merit point. So that's why I need you guys to show me your work. Because if you make one silly mistake somewhere, I can still give you a merit. If you don't show me any working and you just wrote down your final answer, and I have no idea how you pulled that number out of the air, I'm not going to be able to help you. And see, the achieved is one step of the calculation correct. So try to do the whole thing through with your best guess. I can give you a achieve point. So like, for example, if you knew you needed to convert from amount to mass, you showed me that equation and you plugged in some numbers, I could tell that you knew one of the steps of the process. Okay? Show your work. Take a guess. All right. The first part of this question I haven't actually had a chance to talk about because I wanted to go over the calculation first. So one of the things that is a common misconception when we talk about thermochemistry is that for some reason people think exothermic reactions are always spontaneous and endothermic reactions are always non-spontaneous. Do you guys know what I mean by spontaneity? Like it happens without any sort of like extra input. So what we have to keep in mind is that that is not the case. It is dependent on something else known as entropy, which is referring to the disorder that will then be caused. And now, unfortunately, I did not grab more paper, so I'm just going to write on the back, and it's going to be a very mismatched looking notes, but that's okay. You guys will cope. All right. So the thing that we are thinking about today, trying to see what color I haven't used yet, purple, as our next bit of note is entropy. So it's a different word altogether. It looks very similar. It starts with the same letter, ends with the same letter. Not terribly helpful with that. Entropy. Entropy is referring to the amount of disorder. The state of entropy in our universe and what it's aiming to go is to a state of more disorder, so a state with more entropy. One of the easiest ways that I can kind of show it is like, you know how if you spray perfume in the room, those perfume particles spread out to the rest of the room and they're further and further apart, causing more and more disorder. It's very unlikely for that perfume that I've sprayed to then come suck back into one corner of the room, because that's increasing of the order. So we are trying to go into the state that has more disorder. You can then use this as an excuse to why your room is always messy. It is the natural state of the universe to get more and more disordered. So when we are thinking about whether or not a reaction is spontaneous, we have to balance both the enthalpy, so the energy released or absorbed, and the entropy, the amount of disorder that that reaction will cause once it is completed. We balance this with something known as Gibbs free energy. Let me just grab the equation. I was just looking it up. Gibbs free energy. Gibbs free energy. Where did my picture go? I don't want the YouTube. I just want the equation. All right. So we use Gibbs free energy is what we're going to be thinking about. Gibbs free energy is known as delta G, Gibbs energy, is equal to the enthalpy minus the entropy. So entropy is represented by S. I'm not really sure why that is the case. I think it might probably do with some sort of potential Greek or Latin. Now, the thing to remember about Gibbs free energy is that it is dependent on the temperature of the reaction. So some cases it could be spontaneous, some cases it may not be spontaneous. So T comes into place over there. So that G is Gibbs, the H is your enthalpy, so the heat. The T is the temperature of which this reaction is occurring. And the S is referring to the entropy, or the amount of disorder that will occur. Entropy. Just trying to find that little table I normally write. If it's not here, then I'll just go and find it on images. Cool. No, I don't want that. Okay. If you're not doing thermo, go help move. Let's go. Big, strong boys. Just trying to find a good image so I can recreate it, and I think that's going to be the winner. Okay. All right, I'm just trying to make sure I have this straight in my head. Okay, so some things to keep in mind when we're doing these calculations is that if my delta G equals a negative number, then that's going to be a spontaneous reaction. If my delta G is a positive number, then it's going to be a non-spontaneous reaction. So I'm going to have to put in energy for it. The whole. You can go. Oh, okay. Aren't you so nice? You also want to avoid moving, don't you? All right. So depending on the combination of endothermic, exothermic, and the amount of entropy that's going to be increased or decreased, along with the temperature, that's going to decide whether or not you get a positive or a negative number. So if I have an exothermic reaction, and that exothermic reaction increases the entropy, if I have that combination, it will always be spontaneous. Yeah, because I'll always get a negative number. Because the enthalpy would be negative, and it's going to subtract a negative number as well. So since I'm doing a negative number minus a negative number, it's always going to be a negative number. Math. Yeah? So we have negative and a negative. It's going to always be spontaneous. I'm kind of squishing things now because I've run out of space and I don't have my paper. All right. What I could have as well is I could have an endothermic reaction. If that endothermic reaction, so that's going to be a positive number right now. But if this combination of numbers is greater than the enthalpy, it'll still be spontaneous. So if I have an endothermic reaction, but a large T delta S, this will result in a negative number. So that will be spontaneous. So that's how you can have an endothermic reaction that is spontaneous. So even though it's cold and it's absorbing heat energy, it can still happen spontaneously and automatically because of the amount of disorder that is being caused and the temperature that it's occurring at. You good? If I have an endothermic reaction and my entropy is decreasing, I have more order, and a low temperature, I would have a positive number minus a small negative number, so I should end up with a positive number. So I have endo, and I have a small T delta S. This should then result in me getting a positive number. So that will be non-spontaneous. And I'm trying to think what's the last one. Exothermic with a small amount of entropy. Yeah, that one was the last combination. So I could have an exothermic reaction. But if that exothermic reaction decreases the entropy, so there's more order, that could result in a non-spontaneous one as well. More order. So it's more order. Are we okay with that? It's kind of a crash course in what we're talking about. Okay. So going back to this question here, this one wants you to justify in terms of entropy the changes to the system and the surroundings and why the reaction then is still spontaneous. So even though this is an endothermic reaction, why is this still a spontaneous reaction? So if we look at the marking schedule to get an idea of what they're looking for, we are looking for the fact that, first off, when you dissolve an ionic compound, the ionic compound is very structured with that 3D lattice. with the positive and negative alternating back and forth. The moment I dissolve it, I am then losing that nice 3D structure. And by losing that nice 3D structure, I now have more disorder, so more entropy. The entropy of the system increases. I have more chaos occurring. So that's the first thing to think about. The second thing to think about is the endothermic reaction. So that is talking about within the system, so within the reaction. We also need to think about the surroundings as well. So surrounding-wise, this is an endothermic reaction. So I'm absorbing the heat from that surrounding. By doing that, my particles in the air that are around it are slowing down because that kinetic energy is being transferred to my reaction. Since my molecules are moving slower, the entropy of the surroundings has decreased. So I have more order in the surrounding area next to my beaker. So that's what they're referring to by asking about the surroundings versus the system itself. But given that potassium nitrate is a spontaneous reaction, there must be more entropy and disorder in the system than it is what you lose from the surroundings. So the net balance is that the entropy is positive. So more disorder overall in our system. And then if the use gives free energy, that is then kind of explaining the balance between the two. So the enthalpy decreasing means that surrounding is more ordered, but the inside is more disordered. So with the breakdown of these kind of points, the achieved is just recognizing the enthalpy of the system. So understanding that dissolving those ions makes it more disordered, or recognizing that the surroundings is going to be more ordered because you're cooling our air around us down. The merit is then explaining either system. So using your because, therefore, that sort of stuff, or however, it's another good word. The excellence is getting both the surroundings and the system itself. You can also get a merit point if you make a small minor error in your justification. So maybe you do talk about both parts, but you make something that's a little bit, okay? So that's how this point breaks down. This is a very, very, very common question. So be ready to write that justification. Worst case scenario, if you're not sure, just tell me what you think is happening with the system and the surroundings. Take a guess, increase or decrease. Usually one's increasing and one's decreasing. But depends on what's happening. Cool. All right, that's us. We are done. There's no more chemistry for me to teach you.